Hello friends, let's look at binary to decimal conversion with some shortcut tricks. We'll also be discussing the ones and twos complement, which is very important nowadays for your exam. So here is an example. This is a number 2432 which we have to convert to binary. So there is a long method which we are all familiar with. Let's try to rehearse through that so that at least we know that much. So that is the basic method. Everyone should know it by now. So what we do is that we successively divide this number 2432 with 2 and we write down the remainders here. So remainders come here, okay? Remainders come here and we are doing successive division. So first division yields 1216 and of course the remainder in this case is 0. So we write down here. Then we again divide by 2 and the answer comes out to be 608 and we write down the remainder which is 0. Then we again divide 608 by 2. So this is successive division, right? So we are dividing continuously. The answer comes out to be 304. Remainder again is 0. Again we divide. Answer comes out to be 152. Remainder is 0. Again we divide. Answer comes out to be 76. And of course the remainder is again 0. Again we divide. Answer comes out to be 38. Again remainder is 0. So notice that remainders would be 0 anytime this number is even, which we would expect. Again, answer comes out to be 19, remainder remains 0. Now this time, this number 19 is odd. So we would expect that the remainder would be 1, and of course it is 1. So 2 9s are 18, 1 is remainder which comes out to be here. Then we divide 9 by 2, so 2 4s are 8, and of course 1 remains. Then we divide 4 with 2, answer comes out to be 2, remainder is 0. Then we divide this 2 with 2 and of course the remainder is 0. 2 1s are 2, right? So this 1 comes here and we include this one when we form the binary number. So the binary number becomes, we start from this side. So it is 1 0 0 1 1 and then so many zeros, 1 2 3 4 5 6 7 zeros, okay? 7 zeros. So this is our binary number. So we know that now. Now let's try to find the same answer, right? Let's try to solve the same problem, but this time we'll do it fast. And how do we do that? Notice that I have written a very large binary number here. It is the 11111, this is the binary number. Now each of these binary digits has a corresponding decimal value. We know that much, right? So for example, this one has a binary, it has a decimal value. This is a binary one. It has a decimal value of 2 raised to power 0, which is 1. This one has a binary value of a decimal value of 2 raised to power 1, which is 2. This is 2 raised to power 2. This is 2 raised to power 3, and so on and so forth. So the decimal values of these binary digits you have to remember, right? So this is the only thing you have to remember. 2048 is sufficient. Most of the questions can be solved using that. If you want to remember other values like 4096, so on and so forth, you can do that too. But at least this much you have to remember. And once you memorize these, then it becomes really very easy. So how? Look at this number 2432. 2432, the largest binary digit from these which can be subtracted from this number is 2048. So of course we are trying to form this number 2048 by combining these digits. These are the digits, okay, and there is a corresponding location of this digit. So this is 1, this is 2, this is 3rd, 4th, 5, 6, 7, 8, 9, 10 and 11. So this 11th digit would be 1 because 2048 is smaller than 2432. The next number would be 4096, so that becomes larger. So of course that cannot be included. So 2432 must have 2048, so that digit becomes 1. What is the next binary digit which can now be accommodated? So I'll do this 2432 minus 2048. What is the answer? This would be 8, right? So this would be 12 and this would be 8, 384. What is the next digit? Of course 256 can now be accommodated. So we'll put 0 0 here, we don't need these. And 256 can be accommodated, so 256 I'll subtract and then what happens? 8 would come here, 5, 6, 7, so 2 would come here, and then 128. So I would put 1 here, and of course 128 can be accommodated because 128 is here. And now as soon as I subtract 128, this is my remainder 128 from the digit 128 which I have included in my binary number, I get 0. So no other digit from here is necessary, and other digits now become 0. So 256, 128 I have included, 2048 I have included, and these three combine to form 2432. Other numbers become 0. 2, 3, 4, 5, 6, 7. We know it from our last exercise also that this number should be 7. So this was the easy method, right? So once you start practicing using this method, this would become easier because no division is involved. Even faster method would be to try to find out the digits from here directly by adding the digits from here. So 2048 I can add, then 256 I can add to 2048, and then 128 I can add to, and I would know that 2432 can be formed using that, and I don't even have to do the subtraction. So that would be even faster. But of course this method is using the combination of digits from here. This method is faster than the long division method because no division is involved. Now let's try to find out, go other way around, how do I convert this number, this binary number to decimal? One of the way would be, of course, we write down the indices corresponding to this 5, 6 and 7, and then what do we do? It will be 2 raised to power 7. So this is the 7th power of 2. This digit corresponds to 6th power of 2, and then of course what else is 1? 4 and 3, so 2 raised to power 4 plus 2 raised to power 3, and of course 2 raised to power 0, which is 1. So one of the method would be this. Now of course if I remember 2 raised to power 7, 2 raised to power 6, then it becomes easier, right? Or I can use this table if I have memorized it, and I can directly write the values from here. So this is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8, and I don't even have to go. So this will be 128 plus 2 raised to power 6 I can get from here, 64, plus of course this is also there, 2 raised to power 4, 16 and 8, and then finally 1. So if you calculate this answer would come out to be 217. So if I remember these powers essentially, then my mathematics becomes very, very simple, and you don't have to go much. You can essentially remember till 2048, and that should be sufficient for most of the questions. Now of course if we are talking about integers, right, so far we have looked at the numbers which can only be positive. These are unsigned numbers, they can only be positive, and as long as we are in this unsigned domain, the numbers cannot be negative, then this method works out to be fine. I can use this method, I can use long division, I can use this fast trick where I use the this table to convert from binary to decimal and vice versa. But as soon as I come to integer domain, that is, integer means I can have numbers which are both positive as well as negative. So as soon as I come to that domain, I need to think about other ways of representing those numbers. So in machines, in computers, the negative numbers are represented using 3 methods. So there are 3 methods of representing a number. Let's take a simple example. My number is 101. What is the value of this number? I can quickly find out. This digit represents a decimal value of 1. This is decimal value of 2. This is the decimal value of 4. So the value of this number is 5. The binary value is 5. Of course, this binary value 5 is positive. We know that. Similar to decimal numbers, I can add as many zeros as I want in the binary number without changing the value. So as long as the value is positive, I can add as many zeros as I want towards the left, and it wouldn't change the value of this number. We know that. What happens if I want to represent, instead of this plus 5, I want to represent minus 5? Right? So I am not trying to represent plus 5, I am trying to represent minus 5. One of the method is to use sign magnitude. What does that mean? It means that the lower 3 digits, let's say that I have 5 digit, let's say I have 5 digit machine. So my machine is made up of 5 bits. My registers, my memory, everything has 5 bits, and I want to represent all the numbers using these 5 bits. So these 5 bits, what I will do is, the lower 4 bits I will use to represent the magnitude of my number. So I will use the lower 4 bits to represent 5, which is the magnitude. To indicate whether this is positive or negative, I will use another bit here, the 5th bit, and this is known as sign magnitude. So the 5th bit, if it's 0, it is positive. If it is 1, then it becomes a negative number. So minus 5 is just this bit changed to 1. So it is 1 0 1 0 1. If this bit was 0, then it would be plus 5. Very simple. Second method of doing the same thing, right? Doing the same thing would be, I represent, so this is the sign magnitude method, that is the first method. The second method is ones complement method. What would that be? I write my plus 5, which is, okay, in a 5-bit machine, we are using a 5-bit machine, so we have to represent all the numbers using 5 bits. I can add as many zeros as I want, right? So this becomes 0 0 1 0 1. So this is the plus 5. As soon as I want to make it minus 5, what do? I flip each bit. So this 0 becomes 1, this 0 also becomes 1, this one becomes 0, this 0 becomes 1, and this one becomes 0. So in sign magnitude, my minus 5 was and here my minus 5 becomes in the ones complement. My minus 5 becomes this. So this is the ones complement. And how did I do that? I flipped each bit to arrive here. This is the simple method. Another method, a slightly more complicated method, is 2's complement. And what do I do to find the 2's complement? 2's complement is found out by using the ones complement, that is the number found by flipping each of the bits and then adding 1 to it. Very, very simple, right? So I am adding 1. And notice that ones complement, 2's complement, sign magnitude, they are only used for negative numbers. So I am trying to find minus 5 here. That is what I am trying to find. If I was finding plus 5, it would remain same, right? It would remain same in all of these machines. Whether it is in all the representations, sign magnitude, ones complement, 2's complement, the plus 5, it remains the same. The positive numbers are not affected at all. Only the negative numbers are affected. So the 2's complement becomes, I add 1 to the ones complement. Sorry. And this is the 2's complement representation. 1 1 0 1 1. Right? So this is the 2's complement representation of the same number minus 5. So what do we notice from here? One thing that we straight away can say is that in all these representations, negative numbers have a MSB, the highest bit is 1. That is the first thing we notice. This is minus 5, this is 1's complement minus 5, and this is 2's complement minus 5. Same number, minus 5, represented in different ways in the different methods. Common thing is, if the MSB, the most significant bit, the leftmost bit is 1 in all the cases. That is the common thing. Of course, another important thing is the positive numbers in all the representations remain the same. They don't change, and that is same as 101. That is the positive representation of plus 5. Now, let's try to find out what the value of this number would be. Okay, so what does this number mean in various representations? The first thing we notice is that the MSB, the leftmost digit is 1, so of course it's a negative number. Okay, in sign magnitude, we already know that if this MSB is 1, it becomes negative, and this is 5, so this becomes minus 5. What is the value in? So this is the sign magnitude value, right? So if this representation was sign magnitude, the value of 10101 would be minus 5. What would be the value of this number 10101 if it was one's complement? Easy to find out. Again, the MSB is 1, so of course for one's complement the value would be minus, and then the magnitude, what does this minus, how much minus is it, how much negative it is, I can find by complementing this number. I flip the bits again, so I do the reverse operation. To form one's complement, I flip the bits, Now I am doing the reverse operation. I am flipping the bits again to find out the value. So this becomes 0 1 0 1 0, and this value is nothing but 8. This is 8. The value of this digit is 8 in decimal, and the value of this digit is 2. So this becomes minus 10. This is the ones complement. And now let's try to find out the twos complement. So what would be the twos complement value? That is again very simple. What do I do? To find the twos complement, what did I do? I used the ones complement and I added 1. So this time I subtract 1. I am doing just the reverse. I have to go other way around it. So it's from decimal to binary, I added 1 in the twos complement case. To go from the twos complement representation, I need to subtract 1. So first thing I do is I subtract 1. So of course, as soon as I subtract 1, this value becomes 1 0 1 0 0. And now what do? I flip the bits again. So this becomes the ones complement representation. As soon as I subtract 1, I arrive at ones complement. And now I flip the bits again. And the value of this number is nothing but 8 plus 2 plus 1, which is 11. So this is minus 11. Right? So the value in twos complement is minus 11. Let's take some more examples and it will become very clear. Again, try to find out the value of 2 digits. Minus 15, we'll try to find out the sign magnitude representation. What the sign magnitude representation is. So first we find out the sign magnitude, the magnitude of 15 only, right? We ignore the minus. So this value becomes 4 ones, okay? And to indicate a minus, I put a 1 here. So in the MSB, if I put 1, it becomes minus 15. If in the MSB I had put a 0, then this would have been plus 15. Very simple. Let's take another example. Let's try to see what this number would be in. So this is the sign magnitude number. What this number would be in decimal. This number is just for sign. What it tells me is, if it is 1, this is negative, and this is 8, this is 4, this is 2, and this is 1. So 8, 9, 10, 11. So this becomes 11. Of course, if this was 0, then my answer would have been, if this was 0, my answer would have been, so this number would have been plus 11. Since it is 1, my answer become minus 11. So this was the sign magnitude representation. Let's try to do the same thing for negative ones complement number. So let's say I want to represent minus 15 in ones complement. That's my objective. So what do? The first thing I do is I represent plus 15. Plus 15 becomes 0 and then 1 1 1 1. Right? 0 is immaterial. We need to put it though. Okay, so this 0 has to be there. I use 1 1 1 1, which is the representation of 15. I add an additional 0. This is necessary. I need at least 1 0 here. I can put more zeros, but after my last one, I need at least 1 0. Okay, I can put more 0, it doesn't matter. So what I would do is I would just use these. I would add 1 0, and this I will just use this as my 15. One's complement is simply formed, right? Because this is minus 15. To form minus 15, I would just flip the bits. So this is my plus 15, and to form one's complement negative number minus 15, I would just flip the bits. Very simple. See, the thing is, this one, as long as it's there in the MSB, it tells me it's a negative number. If I added more zeros here, more ones would come. So more ones, they could be there. Okay, they don't change the. They just tell me that the number remains negative. Okay, but here we are just using the 5-bit machine. So my machine is only 5 bits. I can represent only 5 bits in that RAM, in the register, in the processor, everywhere in the machine. There are only 5 bits. So I need at least 5 bits, but in the 5th bit there is a 0. So I put a 1 there, and this becomes the negative representation, or the one's complement representation of minus 15. Let's go reverse, which is where a lot of students have problem. So if I have 1 1 0 1 1, how do I convert it to normal number, in the decimal number. So this is 1's complement. Here the MSB is 1. What does that mean? It means it is a negative number and it's 1's complement. So what would I do? I would flip the bits to obtain the positive number. So this is what I would do. And of course, as soon as I flip the bits, this becomes number 4. Of course, this was negative to start with, so I put -4. Very, very simple. Again, if this MSB was 0, then this number would have become 11, similar to the sign magnitude case, right? So positive numbers don't change in any of the representation, only the negative numbers, they change. Now finally, let's move on to the 2's complement. Again, let's take the example of -15. How do I find out the 2's complement of this? It is negative. Okay, that is the first thing we need to do. So the first thing we notice, the representation of +15 is 1 1 1 1. I need to add a 0. At least one bit has to be there after my representation. That is the minimum requirement. And I arrive at a 5-bit number, which is fine. My machine is 5-bit. So this becomes 15. To form the 2's complement, first step I do is flip. I flip the bits. So this becomes, okay. And then what do? I add 1 and number becomes. Right. So this is the 2's complement representation of -15. Okay, this is important. Let's go reverse. Let's go in the other direction. What do? So here is my number 1 1 0 1 1 and it's 2's complement. Again, MSB is 1, so I know that the number is negative. That's the first thing I know. What do? To go from decimal to 2's complement, the first thing I did is flip, and then I added 1. So here I would do just the reverse. First I subtract 1. As soon as I subtract 1, what do I do? What do I get? 1 1 0 1 0. Right? So this is, I go in the reverse direction. First I do -1, so I come here, flip. Okay, I come to this number and then I flip the bits of this number. So it becomes 0 0 1 0 1. And this is, of course, I know this to be 5. And of course, since it was negative to begin with, I put a -5. So that is the 2's complement. Let's take another example. This time it would be 1 1 1 1 0. Negative. So the first thing I know is it is negative. So I do the reverse. First thing I do is I subtract -1. This is 1 0. Decimal value is 2. So as soon as I do -1, the value would become 1. Right? So 2 minus 1 is 1. So this becomes 0 1. Right? So this is 2. This is 1. -1 has been done, and now I do the flip. Right, so this is, I am doing the flip now, and this becomes 0 0 0 1 0, and the answer becomes 2. Of course, the number was negative, so it has to be -2. So notice what I am doing here is I am first subtracting 1 and doing the flip. If I were to go from -2 to the corresponding representation, 2's complement representation, I would have done the same operations, but the inverse operations, right? So I would do flip and then do the +1. Now, again, remember that if the numbers are not, 2's complement is given to you, let's say the same thing is given to you, but the MSB, the topmost digit is not 1, it is 0. Then you don't have to do anything. You can simply write that this number's decimal value, right? We need to find only the decimal value. It would not be negative. It would simply come out to be 1110, which is 2, 4 and 8. This would come out to be 14. Simply, right? In all the representations, whether it be 2's complement, 1's complement or sign magnitude, it would remain 14 if this number is 0. If this number is 1, then we have to do whether it's 2's complement, 1's complement, and apply the appropriate method. So hope this was clear. In the next class, we would discuss fractions. How do we represent fractions in binary, and we'll try to find out again some quick methods of converting to and fro fractions, and we'll also discuss the negative fractions. Thank you.